Welcome back to differential equations. In this video, we're going to talk about the driven spring. So in the last few videos, we've been looking at non-homogeneous second-order differential equations. Let's try that with a skinnier marker. A times y double prime plus b times y prime plus c times y is equal to some function f of t. And I've referred to this function a couple of times as a driving function. And in this video, I want to talk about why we call it that, what we mean by that, and what's going on here. All right. So I've talked several times about the relationship between the second order differential equation and the spring. If we have a spring with a mass at the end, the spring constant K is related to our C, the mass is our A, and we can set up that B as a drag force if we put the spring into a liquid or something like that. So what does f of t represent in this case? Well, the idea of f of t is instead of having the spring kind of attached, fixed to the ceiling somewhere, what if somebody was holding the spring and shaking it? Well, somebody shaking the spring would cause the spring to oscillate and possibly to oscillate wildly. There's a lot you can do with this idea. Anyone who is going onward to study mechanics, you'll start looking at the ideas of resonance and hitting that oscillation at the correct rate in order for some interesting things to happen. But for our purposes right now, I just want you to think about that. If we have this, let me get my head out of the way so I can start writing these down. If I have this as Newton's law, right? F equals ma. We saw that we had a spring force and a drag force. And now I'm going to introduce a third force, which I'm going to call F sub A. And A is, of course, y double prime. All right, so my spring force was minus ky. My drag force was minus beta y prime. And my applied force is going to change over time, f of t. Right? We generally write that as a capital F, and then when we rearrange, we divide by m. So that applied force is what we're adding in. So now we have some idea of what is happening, and we can talk about this in terms of an application. All right, so I want to consider a mass and spring system with a negligible drag attached to a motor. I don't need to be in the way here. Which oscillates at a period of 2 pi over 3. All right, so we've got our fixed ceiling. We've got a motor attached to that fixed ceiling. I put kind of a small sine wave on it to indicate that it's oscillating. We've got a spring hanging below that. We've got a mass hanging below that. If I set m equals 1 and k equals 1, just to get some really easy numbers in here, then I've got y double prime plus y is equal to, let's see, period of 2 pi over 3 is going to be some amplitude, which I'll again just call 1 to make my life easier, times the sine of 3t. So there is a differential equation. And when we have a differential equation, we can always find a general solution. But when it comes to an application like this, we generally have more than that. So let's look at some initial value problems and some particular solutions as ways of building up. I'm going to start with the simplest one. I have a spring that is sitting there doing nothing, and then all of a sudden, it starts shaking. And so my initial conditions in that case are going to be that y of 0 is equal to 0 and y prime of 0 is equal to 0. Here we have an initial value problem to work with. All right, so first, solving the differential equation. Well, first, solving the corresponding homogeneous equation. In this case, that means that y double prime plus y is equal to 0. We can solve this using the method of characteristics. Write down the characteristic equation, which is going to be c squared plus 1 is equal to 0, which gives us that c is equal to negative 1, or I'm sorry, c squared is equal to negative 1, and c itself is equal to plus or minus the imaginary number I. So the homogeneous solution, yh of t, is some constant c1 times the cosine of t plus some other constant c2 times the sine of t. Or whenever you have pure imaginary solutions, whatever the coefficient on I is becomes your coefficient on t. In this case, the coefficient is 1, so we don't even have to write anything down. Step 2 is to guess a particular solution. If I scroll back up and look at my differential equation, my driving function, sine of 3t, is a trig function. And whenever we have a driving function that is a trig function, we guess yp is going to be some coefficient a times the sine of 3t plus possibly some other coefficient b times the cosine of 3t. We take the derivatives of this thing. Yp prime is 3a cosine of 3t minus 3b sine of 3t, and yp double prime is negative 9a sine of 3t minus 9b cosine of 3t. Substitute those particular solutions into the original differential equation. combine some like terms, and then make that assumption that in order for this to work for every value of t, it must be the case that corresponding coefficients are equal. So I get that negative 8a is equal to 1 and negative 8b is equal to 0, which turns into a itself is negative 1/8 and b itself is 0, giving me the particular solution y p of t is equal to negative 1/8 sine of 3t. All right. Now we can write the general solution. Y of t is going to be the solution to the homogeneous case, c1 sine of t plus c2 cosine of t plus the particular solution minus 1/8 sine of 3t. But this was not just a differential equation to solve, this was an initial value problem. So the next thing we want to do is use our initial conditions. Our initial conditions, remember, said that y of 0 is equal to 0 and y prime of 0 is also equal to 0. So we substitute in y of 0. Sine of 0 is 0, cosine of 0 is 1. So we get that 0 is c2. And that whole middle term goes away, which makes our lives a little bit easier. So now y of t is c1 sine of t minus 1/8 sine of 3t. And if we're lucky, we can figure out what c1 is using the second initial condition. So y prime of t, just differentiating here, is going to be c1 cosine of t minus 3/8 cosine of 3t. And then we can evaluate that on our second initial condition. Y prime of 0 is going to be equal to c1 times the cosine of 0. Cosine of 0 is 1, minus 3/8 times the cosine of 0. Cosine of 0 is still 1. That gives me that c1 is 3/8. Plug that back into my solution, and I get that y of t is 3/8 times the sine of t minus 1/8 times the sine of 3t. All right. Given this particular spring and this particular frequency of oscillation of the motor, we're going to end up with a oscillation in the spring that is going to have these two modes kind of fighting with each other. Sometimes they will overlap nicely, sometimes they will fight against each other, and you'll have some kind of interesting motion come out of that. Just to take a look at how the initial conditions affect things, what if we had slightly different initial conditions? All right, so the same differential equation, y double prime plus y equals sine of 3t. The initial conditions now are going to be y of 0 equals 2 and y prime of 0 equals 1. So this time, the situation starts with the spring in motion and pushed away. Right? Usually when we think about initial conditions in the spring, we're thinking about the fixed spring, which gives us a chance to grab the spring, move it, and throw it with some force as the initial condition. In the case of the driven spring, generally the picture that I tend to think of is the spring is in motion, it is shaking, and we're taking a snapshot at some point in time, and we're looking at what its position and speed are at that point in time, and we're calling that our starting point. All right, so a different way of interpreting the initial condition, but still the same idea. What does the spring look like it's doing, its position and its speed when we start, and can we use that to build out from there? All right. I can save us a lot of work because the initial conditions don't show up until the end. Solving the differential equation itself, finding the general solution, is going to work exactly the same. We're going to have C1 times the sine of t plus C2 times the cosine of t minus 1/8 times the sine of 3t. That has not changed at all. The thing that has changed is what happens when we evaluate at our initial conditions. Y of 0 is going to be C1 times the sine of 0 plus C2 times the cosine of 0 minus 1/8 times the sine of 0. Sine of 0 is still 0. Cosine of 0 is still 1. So I get, in this case, that C2 must be 2. Right? Substitute that value of C2 back into the general solution, and then differentiate so we can use the second initial condition. Derivative of sine of t is cosine of t. Derivative of cosine of t is the minus of sine of t. And derivative of sine of 3t is 3 times the cosine of 3t. Then evaluate using the second initial condition. Y prime of 0 is c1 times the cosine of 0 minus 2 times the sine of 0 minus 3/8 times the cosine of 0. The initial condition said that y prime of 0 is equal to 1, cosine of 0 is 1, sine of 0 is 0, cosine of 0 is still 1. All right, I get that 1 plus 3/8 is the value of C1, and of course 1 plus 3/8 is 11/8. So plugging that into my general solution here, I get that y of t is 11/8 times the sine of t minus 2 times the cosine of t minus 1/8 times the sine of 3t. Right? The same general form, different initial conditions give us a fairly different result, which is hopefully not too unexpected at this point in what you've been studying. There we go. Here is a fairly similar looking situation. I've got y double prime plus 4y is equal to the cosine of 3t, along with two initial conditions. Y of 0 equals 0, y prime of 0 equals 1. I'd like you to take a couple of minutes, work through this differential equation. Once again, you can think about it as a spring system. We have a mass of 1, we have a spring constant of 4, and we have a driving function based on cosine in this case. The difference between sine and cosine is what the position looks like when you start the motor up. All right, but take a couple of minutes, see what you can do with this initial value problem, and I'll see you in the next video.